Good afternoon. I hope you're doing well. My name is Fernando M. Gomez, and this is a group project with Ruben Vallejo on defining infinity concerning the Cantor set. The Cantor set is a very useful idea and tool that has been used to break down the idea of infinity. While defining infinity can be a difficult task, it is something doable according to a mathematician, which we will talk about in due time. This is from TAMU, the College of Arts and Sciences, and the Departments of Mathematics and Physics. And it was presented to you by the use of LaTeX and Beamer in that. So we can jump right into it. The purpose of the project is to break down this measurement of infinity concerning the Cantor set. What is the Cantor set? Well, it is important to note that the mathematical operation interprets various sizes of infinity. It's interesting because it's a method and it has properties, and it draws upon the distinct concepts of countable sets, uncountable sets, infinitely countable sets, and finite sets. Cantor sets really can settle into any sort of mathematical analysis, and thus it is very important to understand the concept behind it as well as its application directly to the real world. A short introduction is that when we delve into the Cantor set, it's important to understand the different sets, types, and their measurements. For example, two different sets can be considered equivalent when they come to be the same number of numbers within that set. Very different to considering a set of irrational or rational numbers, which includes a very, very large spectrum. In this case, it becomes uncountable. There are different kinds of uncountable and countable, infinitely countable and infinitely uncountable. For example, there exists a story or parable which is called the Infinite Hotel. What is this Infinite Hotel paradox? What does it talk about? Well, the Infinite Hotel is an imaginary hotel where it has infinitely many rooms, and there is a very expertise manager who happens to have very great experience and knowledge in the field. Interestingly enough, one day a bus arrives with infinitely many tourists. Now, bear with me, I understand infinitely can be a hard concept to grasp, but infinitely many tourists arrive to that location, and so the manager tries to accommodate the newcomers by moving every other guest in the hotel one room over. We can denote each room number as n, and so in this case, simply put, each room number, n, is added to 1. Each room is shifted, or each guest is shifted to each next room, and the newcomers are ingressed into those new rooms. Take, for example, perhaps room number 43 would now be a guest at room number 44. But it's interesting to note that imagine, or in this case, we can allow a new bus of infinitely more or new guests. Now, these guests are accommodated into the hotel in the following way. Since every other room is occupied, what the manager decides to do is to disoccupy every even number. How? Well, every number is multiplied by 2. Using the same definition of n per room or guest room number, in this case, 2 times n would help or allow each even or odd room number to be disoccupied for the new guests. So in the case of room 4, or the guests living at room 4, they would go to room 8. And so now room 4 is available, and whoever is in room 8 times 2 is 16, would move to room 16, and so on. And this is very, very smart because, again, the manager, which is accommodating an infinitely big hotel, is allowing infinitely more new customers to be in that new hotel. And the hotel obviously has infinitely many money and will continue to generate exact money. Now, why is this such an important story or such an important parable? Well, the infinite hotel illustrates infinite sets in almost their whole entirety. And it stems also into providing how complex it can be to define infinity. And the richness principle can come into play as that method of understanding. And it's that if there are more items than containers, at least one container will hold more than one item. Now, to put an end to the story of the infinite hotel, it's interesting to note that it is infinitely countable, unless we would start counting rational room numbers, which would be very interesting to look at. In the case of room number 1/2, the person would have half the space of a regular room. And perhaps a room pi would have a 3.14 bigger room than the rest. Now that would be infinitely uncountable. The richness principle indicates that there is a furthermore idea in the case of infinity. If there are more items, again, in containers, at least one container will hold more than one item. And a good example for this would be musical chairs. Now, just as a refresher, perhaps it's been a while since we've played. Musical chairs are played by setting up a number of seats, while a number of participants with one more are included into the activity. And while the song plays, they're walking or dancing around these chairs before finally sitting at a chair that they have designated. However, of course, there will be one person left over, which in this case loses and sits back down at another seat, while the rest of the people who chose those first seats are allowed to remain in the game. The richness principle is very similar. If there are more items than containers, in this case, if there are more people than chairs, then there will be one chair, or in this case, there will be one extra person that will not be able to take that seat. And this continues on with the idea of infinity. There is a one-to-one correspondence with infinitely countable sets, but there is no one-to-one correspondence with even smaller sets. And this is where it gets fun, because now we go into the actual definition of the Cantor set. Countable and uncountable sets, of course, show or are demonstrated by Cantor. And the proofs differentiate between finite, countably infinite, and uncountable sets, which I was mentioning earlier. George Cantor used his contributions, which were exceptionally foundational in providing insight into the infinite, especially concerning the set of real numbers. Real numbers include 0 and so on, but it's interesting because Cantor considers numbers within those numbers. Let me explain. Now, countably infinite is an infinite set A, let's say it is called A, is countably infinite if the set A includes all the natural numbers. So if we were to count from 0 to 100, only the natural numbers, that would include 0, 1, 2, 3, 4, 5, and so on until we get to 8, 9, and 10. If we were to count from 0 to 1000, we could count from 0, 1, 2, 3, 4, and so on. Moreover, if we were to count from 0 to infinity only natural numbers, it is also countable. Although our finite thinking mind is incapable of counting so many numbers, in the a concept, it is valuable to note that it is countably infinite. Despite it being infinite, it is countable. However, a set is uncountable if it is not finite or countably infinite. This is where the Cantor set comes in. The Cantor set is uncountable. Cardinality of a finite set A is 0 if A is empty, and n if A is approximately 1 through n. This refers to what I was saying before. 0, 1, 2, and 3 up to 100 would be a countable set. The Cantor set, however, involves such a small space between 0 and 1 to be uncountable. How? We can construct our own Cantor set in the following way. First, we think about a set, and we let set I equal from 0 to 1, inclusive. First, we remove the middle thirds. This would only leave us 1/3 and 2/3 of 1, which is also 0 through 3rd, and 2/3 through 1. At each stage n, however, we remove the middle third from each interval. In the case of the second interval, each length being 1/3 would leave us with 1/6 and 2/6, or 3/9, 1/9, 2/9, and so on. In the image, we see a great example of this, of how to construct the Cantor set. In the first stage, we see the second middle third being removed, and now we have 2 lines. And in the second stage, for E sub 2, we notice that each of those lines were separated into 3 pieces with a middle being removed. How would we be able to define the length of the set? Well, since E is the intersection starting from n equals 1 up to infinity, with E being a sub of n, the length of E sub n tends to 0 as n approaches infinity. Thus, the Cantor set E has a length of 0. This isn't expanded to multiple areas. Numbers in E must have ternary representations consisting only of zeros and twos. We notice that 0 is entirely made of zeros. 1 can include zeros and twos, 1/3 0 and 0 twos, and 2/3 0 and 2 0. We can prove the uncountability of the Cantor set by considering that each point in the Cantor set has a ternary expansion using only zeros and twos, which establishes a 1-to-1 correspondence between points in E and binary sequences of 0 and 2. But since the set of all such sequences is uncountable, E, the Cantor set, is uncountable. Now what happens if instead of removing the middle third, we remove a different fraction of each interval? What properties would this new set exhibit? Well, we would notice more common fractions. Still, we would also have an uncountable set, since each value or each interim will become smaller over time. So this project was able to delve into the world of finite and infinite sets, into countable and uncountable sets, and through mathematical method of proof, we established a general definition of the Cantor set, which happened to be uncountable. The techniques are helpful in understanding the depth and the interconnections of mathematical reasoning to prove the unaccountability of the Cantor set. It would be important or valuable to delve deeper into the applications of the Cantor set outside only this project, because the exploration of the nature of infinity and its applications across other disciplines encourage broader topics and could potentially provide us with new innovations. Seeing that the universe is such an expansive space of continuance and power and construction, considering the Cantor set as something to be able to grasp the concept of the expanding universe is useful to the space exploration. And that is the conclusion of the Cantor set. We would like to express our gratitude to our advisor and to all the people in the Department of Mathematics and Physics who support it with respect.